Good afternoon and welcome to this webinar, Decarbonization, What, Where, and How to Make an Impact. I'm your moderator, Kyle Gregero, Editor-Director of Engineered Systems. This event, brought to you by Engineered Systems, is sponsored by Trane. Thanks for joining us today. Today's presenters are Charles Jellin, Jackie Supko, and Matt Brunner, all from Trane Commercial. Charles is the Decarbonization Program Manager for Trane Commercial and is based out of La Crosse, Wisconsin. He has been involved in the development and support of HVAC systems for Trane since 2012, with expertise in the areas of hydronic systems, refrigerants, system modeling, and decarbonized system designs, including the electrification of heating. As the Decarbonization Program Manager, he has responsibility for key account decarbonization and customer project support across North America. Jackie is a product manager based out of Colorado and has worked for Trane supporting chillers since 1997. Currently, she is a product manager for the Arctic integration with a focus on products that support electrification. During her time at Trane, she has held several positions, including technical support engineer, as well as water-cooled and air-cooled chiller product manager, which gives her a great foundation to support customers with new applied technologies and electrification solutions. Matt leads the VRF team for Trane New England as the ductless sales specialist and is based out of the Boston office. Since 2016, he has been involved in bringing VRF to the greater Boston area and has watched the market grow from a niche product to a crucial piece of decarbonization initiatives. Strategic electrification is critical to policy at its local and state level, and Matt assists consulting engineers and architects in adapting sustainable, all-electric designs. Don't forget to submit your questions, and later in this program, our presenters will address as many as possible. Today's event is being recorded and archived on esmagazine.com/webinars. And now I'm excited to turn over to today's first presenter. Go ahead, Charles.
So thank you very much for the introduction there, and thanks everybody for jumping on. Today we're going to go through a couple different things that revolve around decarbonization. So we're going to start with some of the basics around what it is. We're going to talk a little bit about some of the policy around the country that's pushing decarbonization initiatives. And then we're going to get into some of the solutions available for decarbonization, namely electrification, energy efficiency, and refrigerant management. And then towards the end, we're going to have two other speakers hop on, and we're going to talk about some specifics around some technologies that designers are choosing to go with right now. All right, but to start, we want to get into more of the basics of what is decarbonization. And this graph that you see on the screen here, or this chart you see on the screen, this is from Project Drawdown. And if you're interested in any of the background information around decarbonization, they do a great job of consolidating information and bringing it into graphics like this to help tell the story. So what you're seeing here on the left-hand side is all of our sources of emissions, and they bucket them into big sectors. So on the far left, you see electricity production. So that's all the emissions associated with the generation of electricity from utilities. So burning natural gas and burning coal to produce electricity. Then we got food and ag, industrial, transportation, down to buildings. Buildings looks a little small there, but a big percentage of what buildings use for emissions is pulled from electricity, which shows up in that electricity production. All right, so we have all these sources of emissions, and that all goes into our atmosphere. The nice thing about what we have in our environment is we have natural sinks. We have things, vegetation, plants, coral reef that use CO2 in their life cycle process. And so there are these natural sinks. The problem that we're facing today is we are out of sync with our environment to the tune of 59%. So 59% of what we emit into our atmosphere has no natural sink. All right, and so that carbon emission stays in our atmosphere, leads to global warming, leads to climate change that we're seeing around the globe. All right, and so that's our imperative here. When we talk about decarbonization, we're looking at the left-hand side of this chart, all of our current sources, and we're trying to figure out how do we lower our emissions in these sectors. All right, and in HVAC, we obviously have a big part to play in buildings as well as industry. So next, we're gonna start this off with a question. And the question we're gonna ask is in the area, in the region that you're from, have decarb policies been enacted in your area? So we're going to open it up here. We're going to give everybody about 30 seconds to respond, and then we'll take a look at the poll results and talk through them. All right. We've got most of the votes in by now. So we're going to switch over, and here's what we came up with. So 104 have already addressing in our design, so already there. In the middle there, 132, 35% not yet, but changes are coming soon, and 36% no, not in the near term. All right, that's a really interesting spread and not unexpected. So if we look around the country, what this chart is showing you here is, well, the first one in the top right, 325 cities have stated a commitment to some type of climate action. That's usually pretty generic. It's pretty broad. A local county or a local city will say, we are committed to reducing our emissions. But until they put a quantifiable reduction goal against it, it doesn't really have a lot of teeth. And so that next bullet is a big one. 18 of the top 20 most populated cities in the US have a quantifiable emission reduction goal. And the reason that's important is it's the jumping off point for local policy to work towards. So once you have that target and people are accountable for it, now we can start to push policy and push programs to start to change the way that we've been designing buildings and systems. Also on this chart is, there's a couple big dots in there with a white cross. These are cities and areas where policy is in place or pending, is looming, but it's actively changing the way that we design systems and design buildings today. And we're seeing a change in the way that HVAC systems are going in. All right, namely electrification, that's a big one, refrigerant management, going to lower GWPs, and just an overall thought process on the carbon output on the back end. So instead of just looking at energy efficiency and do we comply with 90.1 or do we meet a stretch goal, taking it to that next level of looking at the carbon emission profile and projecting that out into the future. Here in the U.S. and for federal policy, there is a lot of action. If you've heard recently in the news about the Paris Agreement, that's been getting a lot of publicity with the current administration. The Obama administration originally signed us up for the Paris Agreement, and then the Trump administration pulled out of it, and then the Biden administration went back in. Not only did they agree to the Paris Agreement and put forward a plan, they doubled down on what we had in the past. So currently today, we are committed to a 50 to 52% emission reduction from 2005 levels by 2030. All right, so that's a big goal in the next 9 years. And so for the current administration, over the next 3 years, we are going to see a major push from the federal government to try to take the first steps towards this big reduction of 50%. All right, what that will include is DOE upgrades for efficiency standards. They'll be revised and revisited. The third bullet there, we're going to talk a little bit more about that, but the EPA was given the authority to regulate high GWP refrigerants, which they had not had in the past. Okay. But when we talk about decarbonization, right, decarb is this umbrella. All right, there's a lot that we can do in terms of reducing carbon emissions. In the HVAC space, if we look at what are our big levers to go after, you can see them on the right there. Energy efficiency, refrigerant management, and electrification. So we're going to spend a little bit of time on each one of these. But before we do that, we're going to ask the team here another question. So the question is which strategy do you think will have the biggest impact on decarbonization? So the answers are going to be electrification, energy efficiency, refrigerant management, and renewable energy. Again, we'll give the audience about 30 seconds here to get their vote in. All right. And here's what the results look like. So 40% say renewable energy, 30% say electrification, 25% energy efficiency, and not surprisingly, refrigerant management came in last there at 3%. Interesting results, right? Renewable energy and electrification go hand in hand, especially if the renewable energy is at the utility scale, the grid scale. Because if we become heavily powered by renewable energy, electrification comes along for the ride, and it makes more sense as we go. Energy efficiency has been a focus for a lot of companies, a lot of organizations for a long time, as long as HVAC has been around. So again, not a surprise there, and that's usually the first stepping stone that people take when they're going down this decarbonization journey is remove waste in your systems, go after energy efficiency, and then move on to the next ones. We're going to talk a little bit about refrigerant management a bit, so I'll save that one. The first topic here is efficiency. And like I said, this has been energy efficiency has been around as long as HVAC has, right? This continually trying to become more efficient. Whenever we're working on a decarbonization project, you'll start to hear terms around where the emission is coming from. And so you hear site emissions, which are scope 1 emissions, or you'll hear source emissions, which are scope 2 emissions. Those are the utility emissions associated with burning natural gas or coal to produce the electricity. Okay. But when we're talking about energy efficiency specifically, we're working in our bucket of what we have available, and that's at the site itself. And the equation to pull down your carbon footprint is straightforward. If you can lower your energy usage, you will lower your carbon footprint, regardless of where you're at in the country. All right. And the opportunities here are all the opportunities we've always had with energy efficiency. So moving to higher efficiency products, moving to higher efficiency systems through controls and optimization or good design principles. Building upgrades, just the building itself, are will have some of the biggest impact on your carbon footprint from anything you can do. Some of the most expensive things you can do as well. But if you can lower your loads in your building, that lowers your consumption of your HVAC equipment and lowers your carbon footprint. So anything with lighting, with windows, any material upgrades like that. And then the last one we have in there, and I've got a slide on Trace 3D Plus coming up, but documentation is key in this area. Whenever a customer comes and says they want to lower their carbon footprint, the first question is always, do you know what your carbon footprint is? Because that's the jumping off point. You can't look. It's hard to have targeted investments in your carbon footprint if you don't know where you're spending your carbon emissions. So everything from it could be as simple as taking your utility bills and turning them into a carbon profile and just sorting between scope 1 and scope 2 emissions. From there, we can start to develop a plan on how you're going to lower both of those. All right? And where Trace can come into play is that racking and stacking projects. If you're going to invest in a lower carbon future, what are those projects that are going to that have the highest return on your carbon investment? And a modeling tool like Trace can help with that. The next area we're going to look at is refrigerants. And just like that poll question, customers see refrigerants having the least tie to decarbonization. Typically, when we talk about decarb, electrification's right at the tip of the tongue, energy efficiency is right there. Refrigerant lags behind. All right, but it has a place to play, and it can have a significant impact. And so we'll take a look at how big. In terms of policy, this is a really broad, changing topic week to week. So if your organization is looking for an update on where the industry stands on this current refrigerant transition, please reach out. We have a lot of information that we can share there. What I'm showing you here is just a snapshot for today. All right, we do not have a federal phase out of specific refrigerants yet. The EPA is working on that right now. All right, but we do have 10 states that have stepped up with their own phase out of high GWP refrigerants in the absence of a federal standard or a federal rule. All right, so the 10 states in green have all phased out R134A and R410A in chillers starting January 1st, 2024. California has gone one step further, and they phased out 410A in unitary equipment in 2025 and VRF equipment in 2026. What I will say is AHRI, which is the common body for HVAC manufacturers, we petitioned as an industry, we petitioned the US EPA to adopt very similar rules as what California has in place. Phasing out chillers in 24, unitary in 25, and VRF in 26. The US EPA did accept that, and we do think that by the end of next year, those rules will be in place across the country. But still more to come there. So in terms of how big of an impact refrigerant can have, we wanted to just boil this down to a single project. All right, on one project, what am I looking at here? In general, the equation at the top is really easy. If you can get to lower GWP refrigerants, you will lower your carbon footprint. What we're showing you with the charts, the height of the chart, or the height of the bar, is metric tons of carbon equivalency for the different refrigerants that you see. Right? And then we put them into kind of the three product buckets or refrigerant pressure buckets that we typically talk about in our industry. So scroll equipment, high pressure on the left, that would be like rooftop unit equipment. In the middle, medium pressure equipment, so either screw or centrifugal. And then on the right, low pressure equipment, typically centrifugal. If I was going to give you an example here, and this is all for 500 tons of cooling capacity. So let's say you had a project where you needed a 500-ton chiller. You could lay out R134A at 500 tons, and that unit would contribute about 850 metric tons of carbon equivalency, meaning the refrigerant that's inside the chiller has 850 tons of carbon. Conversely, depending on where you're at in the world, you could use R1234ZE. In North America, there is 514A and 1233ZD available, and you can see the difference from 850 down to 10 metric tons. All right, so significant impact, especially if there is a carbon driver on the project. If the customer wants to go to a lower carbon future, this is a really easy way to show that you're making an impact. If a customer has a range of assets and they're looking to make a step function change long term, how do I reduce my fugitive emissions of my assets? We've got three things that you can look towards. Number one is service and maintenance. And the big thing we're trying to do here is reduce that catastrophic failure. For the most part, equipment from the factory is pretty leak tight. It does not leak a lot. All right. Where we get into trouble and where you see higher average annual leak rates is because we include the catastrophic failures where you lose an entire charge or you lose the vast majority of the charge in the unit. And so regular scheduled service can help reduce that risk, take it off the books. Okay. The second one there, where it makes sense, transition to next generation refrigerants. All right, so especially in new construction or large major renovation or major retrofit, there are next generation refrigerants available today to help you make that switch. And then the last one there, tracking and reporting. This is twofold. One is for compliance. The second one is just for data analytics on your operation. Compliance, because the US EPA will likely expand their scope of what needs to be reported up through the EPA in terms of leakage. So how much refrigerant you use on an annual basis. So if you have to do that, you have to do that. You got to get those mechanisms in place. The other side of it is just knowing what assets are leaking more than others. If you have a list of assets at your building or your buildings, it would be nice to know which ones are leaking as a percentage more than others. And then you can get in front of that with a scheduled maintenance or a scheduled changeout. All right, so that's it for refrigerant. We're going to move into the last topic here, and this is typically the topic that most people associate with decarbonization, and that's electrification. There is a policy component to this, and it's really, really straightforward. If your local county, in this case, is what I'm showing you on the screen, if your local county has a natural gas ban, they are telling you you must electrify, right? That's essentially what we're going after. So this map is showing you around the country counties that have, in dark red, enacted a natural gas ban, and then in the lighter red there, counties that have proposed a natural gas ban. And then the size of that diamond is the number of building permits that are currently there. All right, so you can see some major cities across the U.S. It's not just on the coast. This is a trend that's moving across the U.S., but it's pointing towards electrification. One thing we want to get across, and if you've dug into this across the U.S., it starts to make sense. But the first time this concept comes up, it's interesting, right? It kind of changes your perspective on energy. And it's this concept that not every watt of electricity is created equally. All right, so the amount of emissions associated with a megawatt of production is dependent on what the local utility has for generating assets. How much natural gas do they burn? How much coal do they burn? And how much renewable energy do they have on their grid? And you can see a really wide spread here. So the darker the shade, the dirtier that grid is. And you can see it goes from everything in Hawaii, which has almost 1,700 pounds of CO2e per megawatt hour of production, down to upstate New York, which is at 232 pounds per megawatt hour. All right, to give you an example of what those asset generation mix looks like. Whoop. For some reason, that one doesn't show up. There it goes. Must have been on a timer. So on the top, you have RFCW, which covers Ohio, Indiana, a little bit of Maryland. And then on the bottom here, you have NYUP, which is upstate New York. These two grids almost touch, but they're totally opposite in what they generate with, what they generate electricity with. So RFCW up here, you can see, is 66% fossil fuel based. And it's got a big chunk of nuclear, 28% nuclear, and then a little bit of renewable energy at the top. Contrast that with NYUP, which only has 27% fossil fuel, 31% nuclear, and then a big hydro chunk there, and then a little bit of other renewables. All right, but this mix gives you that low emission grid compared to something that burns a lot of fossil fuels. So what this means is electrification is a different proposition across the country, right? And we're not necessarily just electrifying for today. Grids across the country are greening up at a rapid pace. So in areas like upstate New York, electrification makes carbon sense today. In areas like RFCW in Ohio, it's basically a neutral proposition today. You're not going to be saving carbon today. But if it's a new construction building, and that building is going to last 30, 40, 50 plus years, there is a bunch of green energy coming the way in the near future. So that building that you electrify today doesn't have to do anything, doesn't have to change its major function. But as the years progress, it keeps getting greener as we go. So again, we're not necessarily electrifying for today. We're electrifying for now and into the future. Talked a little bit about Trace 3D Plus. There's a lot of capability in this space. You can see the different systems that we can model. We can do on-site renewable energy, so both solar, wind, and geothermal. And then, of course, electrification. So comparing the business as usual, maybe chiller boiler scenario to heat pumps, and then looking at the impact of the grid as well as burning natural gas on site to compare your carbon profiles. So a lot of capability in this space. Again, please reach out if you have any questions on this. All right. Before I hand it off to Jackie, there are a lot of solutions for electrification today. All right. You can see some of the big categories: air source heat pumps, water source heat pump, VRF systems, electric resistance, even ground source or waste source systems. There is not a one size fits all. And typically on the projects that we're working on, it's a combination of multiple ones of these to make it happen. All right. And so today we're not going to touch on all these. We're just going to focus in on two. And to kick us off here, Jackie's going to take us through some applied heat pump products.
Great. Thanks, Charlie. Well, we are going to talk about these products and see what kind of solutions we have. But first, we're going to do another poll. And so if you think about the next 12 months and the projects that you have coming up, what solutions are you most likely to incorporate? Are you looking at heat recovery, heat pump, VRF, or maybe something else? So we'll give you a few minutes just to chime in here so we can see some of these results. Well, it looks like we've got most people in. So let's take a look at those results. It looks like heat pump, heat recovery, and VRF. It's a three-way tie. So the great news is we're going to be talking about all of those solutions moving forward. So, we are seeing all kinds of energy needs within buildings. Building designs continue to evolve and improve, and we're moving towards more sustainable solutions. We're really pushing the boundaries of HVAC systems. We're using chillers as heaters. We're recovering heat that we would have typically rejected as waste heat. We're even combining systems to really help us optimize energy use and reduce our carbon footprint. So first, let's talk about heat recovery and heaters. So heat recovery is one of the most simplest solutions for electrification. We're really taking heat that would normally be treated as waste and rejected to a cooling tower, and we're reusing it to satisfy a heating load within our building. Now, while we typically think about heat recovery in water-cooled applications, we can also do partial and full heat recovery in air-cooled chillers as well. This is typically done with a desuperheater or a secondary heat exchanger. We can do better than running a boiler and a chiller at the same time. Within large buildings, we typically have a heating and cooling load all year long. So we can move or export heat from the warm interior of the building and utilize that in the cold exterior of the building, really using that heat energy that we previously would have rejected as waste and using that to reduce our heating load. By doing this, we're reducing our heating load, we're saving money, and we're also helping to reduce our carbon footprint. Now, chillers can also act as heaters. Now, when a chiller is a heater, its primary function is producing heat. So the chiller is looking at a leaving condenser or hot water set point. And that's what it's controlling to. That heater, now we're calling it a chiller. Sometimes we would call it a chiller heater. I've even heard them referred to as cheaters. Its primary function is to provide heat and control off of that hot water set point. A great application for these heaters is in a large chilled water plant. Like I said previously, we almost always have a need for hot and cold water year round. So I'll add this heater to my large chilled water system. The heater is acting as a heater, loading and unloading based on the heating load of the building. And then the cold water that it's producing is sent upstream in the system to help those chillers that are providing the cold water become even more efficient. Adding a heater to a large chilled water system is a must anytime that you have a need for heating, anytime there's a heating load at all. Being efficient is really the key to being successful here. So if we move on and talk about heat pumps. Now, heat pumps can provide hot or cold water. Heat pumps contain a reversing valve within the refrigerant circuit that allows the evaporator and the condenser to switch roles. So when we look at a heat pump heat exchangers, we would like to use the term source and sink versus evaporator and condenser to really describe whether it's either accepting heat or rejecting heat. Now, heat pumps come in a wide variety of sizes. We can also do an air source heat pump or a water source heat pump. Now, when a heat pump is in cooling mode, it operates just like a chiller. It's producing cold water from a cooling load, and it's rejecting heat into that sink. Now, when the heat pump is in heating mode, that reversing valve has changed directions. So our evaporator and condenser, or our source and sink, have switched roles. And we are now providing heat, pulling that from the source, satisfying the load in the building. Heat pumps are great for any building that has a heating load in the winter and a cooling load in the summer. But where can I find BTUs when I don't have a cooling load, or when it's extremely cold outside and I'm not able to pull that from the air using an air source heat pump? Well, geothermal systems are a great option. Connecting those to your HVAC system allows them to either reject or add heat depending on the building's needs at the time. Geothermal loops are proven technology. They've been around for years, and they're a wonderful application to help with your electrification needs. Now, we can also use lakes, rivers, and ponds. This is another source that we can potentially consider, but remember, we do need to look at local jurisdictions and understand just how much energy we need for the project. Now, storm drains and sewers, when I combine that with specialty heat exchangers, that might seem like an odd option. However, they usually have a consistent temperature and work very well as a source of heat. Thermal energy systems are a wonderful solution when I don't have anything natural like a geothermal lakes or storm drains. So that's a great option for us to investigate as well. And don't forget about exhaust air recovery. That's another great option to help find some of those hidden BTUs in your building. Now, this is just a snapshot of some of Trane's heating portfolio. We have heat recovery and heaters available, air-cooled and water-cooled, in a multitude of sizes. We also have a full modular line of products. This includes full heat recovery, partial heat recovery, multi-pipe, and heaters. So anything that you need from a modular standpoint, we've got you covered there. Modular products are great for retrofit as well as new construction. We also have a full line of air source heat pumps, both modular and package, going all the way up to 230 tons of cooling. We have the equipment controls and the support that you need for any of your electrification projects. And with that, I'll turn it over to Matt.
Thanks, Jackie. So when talking about electrification projects, VRF or variable refrigerant flow systems have been really popular for several years. And the way these systems work is you essentially have a condenser or sink on the roof, and then individual indoor units within the space, and you deliver heating and cooling to the space via variable refrigerant flow, as the name entails. So there are several ways in which this kind of really helps. Using the inverter compressor delivers exactly the amount of heat or cooling you need to the space, which prevents cycling, and you can kind of see that on the diagram at the top of the screen here. Whereas a conventional system may bang the compressor on or off, depending on set point. VRF really seeks to hit the set point and keep it close, which keeps tenants more comfortable and also uses less energy, which is a key component of electrification. You can kind of see a diagram of what your general VRF system looks here. So typically you'll have one or several outdoor units, and again, one or several indoor units. Talking under the umbrella of VRF systems, you also kind of include mini splits, which are one-to-one applications you'll tend to see in houses that are also a great electrification option for residential houses. And then the middle piece you see there, the BC controller, is another critical component of VRF systems. What that is that's your branch controller, and that allows for your heat recovery within the space, simultaneous heating and cooling, which is critical because that essentially allows you to reuse heat within the space to cool other spaces, lowering your total load and really, improving the efficiency of the building. So VRF can really be, useful in 3 different ways when it comes to solving electrification challenges. We'll go through 3 of them today. You have efficiency on the left. Again, that inverter-driven compressor really helps with reducing your total load. Heat recovery is integral too, because the less space you have to pull from the outside and the less heat you're ejecting to the outside, the more efficient your system's going to be. As far as low ambient performance, VRF systems have really been tuned for the North American climate now, and this is critical for electrification because you don't have to have a backup gas source with VRF systems in most of the country at this point. And then the third pillar we have here is retrofit ready. So a lot of projects moving forward, with the timeline we're looking at, are going to need to be upgraded, and you're going to be putting a system into an existing building, and VRF is very well suited for that, which we'll discuss. So here we have a diagram kind of showing how your VRF efficiency can really help with an electrification project in a space. You can see the red lines kind of indicate heating zones where you're going to be discharging heat into the spaces via refrigerant, and then cooling zones are your blue lines. So if you think you have a conference room in the middle of the building where big load can generate if there's a meeting, you can pull the heat out of that space and then send it to your branch controller, and then heat will be delivered to the spaces that need heat on the perimeter where you may have windows, for instance. Another benefit of the flexibility of having, heating and cooling in spaces outside of the, efficiency is that, you have additional tenant comfort. So you don't have folks that are in the corner of the building stuck being cold because they are, on the same system as the conference room in the middle. So keeping in mind diversified load profiles really helps when designing VRF systems. If you can maximize where you may have cooling in one space and heating in the other space, because most VRF systems are air source, and what that means is you're going to be drawing, cooling or heating from the outside, and as it gets cooler outside, there's less heat. So if you can source that heat from within the building, you're going to be really improving your efficiency on the whole system. To that note, there are water source VRF systems available. Most of the systems you'll see will be air source just because it's less of a upfront capital cost. And as it gets colder outside, it is harder to draw heat from the outside air just because there's less heat available. So one of the kind of concerns you may have would be, okay, well, how much is it going to cost for me to run my electric heating in the winter? And VRF really is tuned well for this. So if you figure your coefficient of performance is how much heat are you getting per 1 unit of energy with electric resistant heating, where you're just directly using, electricity to heat the space, consider that to be a COP of 1.0. VRF is at a COP of 4.5 at milder conditions, let's call it 47 degrees is where AHRI rates VRF systems, and most VRF systems are rated at a 4.5 COP. So you can figure there, looking at this chart on the right that compares VRF to electric resistant heat or boiler, you're 450% more efficient at 47 degrees as you would be at using a conventional system, just burning fossil fuels or using electric resistant heat. Now you do start to lose some efficiency as you go down the line and it gets cooler outside because there is less heat. So you're going to need to work harder with your compressor to draw it. But at the end of the day, even once you're getting below 0, you're still at a COP of around 2. So you're still being twice as efficient with your VRF system as you would be using natural gas or electric resistant heating. There are a couple other strategies that can be used to kind of boost your efficiency with VRF systems. One of them is called variable evaporator temperature. What this does is you can use a DOAS system to kind of decouple your sensible cooling load from your latent cooling load. Granted, this is more of a cooling side application, but you can boost your VRF efficiency by up to 30% by raising your evaporator temperature. That's a whole other discussion we could talk about a different day, but something to be aware of. Additionally, you have heat recovery, which we already kind of hammered on a little bit. You are reducing the amount of heat you have to draw from the outside, which really can improve your efficiency on the system overall. On the other side of that coin is low ambient performance. So that was kind of a big concern with VRF systems a couple of years ago was, am I going to be able to deliver my heat for these, cold zones? It gets cold in a lot of parts of the US in the winter, and are we going to be able to actually produce it? And the answer today is yes. There's a new technology that's been introduced to most VRF systems at this point called flash injection technology. And what that does is it adds mixed phase refrigerant to your compressor, cooling it down and allowing it to perform better at lower temperatures. You can kind of think of it as like a turbocharger for your VRF system. So as it stands today, Trane and Mitsubishi City multi-systems, as well as most VRF systems, are tuned to produce that heat at very low temperatures. So the map we're showing here is the ASHRAE 5-year data. What this says is for these metro areas, this is as cold as it's been on any given day in the last 5 years. And if you look at our performance charts on the left here, hyperheat systems, which is kind of the cold weather version, flash injection technology, really tuned for your cold weather, produces up to 70% heating at minus 22 degrees Fahrenheit. So that saying is even in Minneapolis in the past 5 years, you still would have been able to get your heat in the middle of winter. And anecdotally, I haven't heard of any situations in my neck of the woods where somebody has been unable to get their heat in the middle of winter. And again, heat recovery also kind of benefits with this. Even if you have a building in the middle of winter, you're probably still going to be generating some heat in the core. You draw the heat out of that and use it in other spaces, and you're going to be improving your performance just because the system still doesn't have to work as hard. Now to get to the retrofit, I kind of alluded to this already, and Charlie did earlier as well. A lot of buildings that are going to be electrification projects are going to be existing projects because we're going to be doing a lot of moving towards electrification in the next 10 years, and you figure the life of a building is much longer than 10 years. So a majority of these projects are going to be electrification in existing buildings moving forward, and VRF is really well suited to that in a number of ways. You don't have to run ductwork into a building for VRF. You're just running refrigerant piping. You don't have to require mechanical space for large equipment. VRF outdoor units are modular, so you can fit them where they fit, and you can also use a variety of different style units to, fit the equipment wherever you can. Another kind of side bonus is a lot of projects, especially in the north, we see these days are schools, for instance. You're adding cooling to buildings that never had cooling before. They want to use these spaces in the summer for programs, for instance. Well, if you install a VRF system, which can both heat and cool to get the cooling, you also have, you're kind of walking them right into electrified heating by giving them a system that can heat as well. Another benefit with VRF is that you can use the controls to connect to a backup heat source. So you can say, okay, we're going to use VRF heating in mild conditions, but then once it gets below, say, 20 degrees and it's really cold out, if we want, we can still use our existing boiler system. And a couple other options. These days, you don't need to use your VRF indoor units either. So say you have existing air source equipment that you want to continue, air handlers, rooftop units, you can tie a VRF coil into that unit and electrify your heating without having to totally get rid of your existing equipment. Looking ahead, we have a couple of other options in the pipeline too that are coming out that we're really excited about. The first one is called Heat 2.0. It's a very clever name. It's an extremely efficient all-electric commercial water heating solution that essentially allows you to finish electrification of your building by providing your hot water with a CO2 refrigerant. So CO2 is actually a great refrigerant in heating applications with a large change in temperature. And obviously it's super environmentally friendly. It's got a GWP of 1 and it provides hot water up to 176 degrees. So that's coming out in some select markets right now, but it's going to be rolled out to the rest of the country pretty soon once we get through this first launch. I'm really excited for it. Another option that's coming out is called hybrid VRF. And what hybrid VRF is it's just like your regular VRF system. You can see the parts and pieces down here on the right. But what it does is it uses a standard VRF outdoor unit and transfers heat with water in a hybrid branch controller. And you're essentially delivering water to all your indoor units. So what this does is this, lowers the cost of installing water piping to your zones instead of refrigerant piping. And you're also reducing the total amount of refrigerant in the building, which helps with the second part of decarbonization we were talking about earlier. So that's going to be coming soon. 2022 is the latest launch date. So keep an eye out for that. And with that, I will be turning it back to Charlie.
All right. Thank you, Matt. So just as a quick wrap here, if we go back to the presentation title, what, where, and how to make an impact. So what is decarbonization? It's reducing our carbon emissions across all sectors. And for us in the HVAC space, that's primarily the built environment. Where? This is happening all over. There are certain countries leading the way, Europe, Canada, and then there are big cities across the US that are going after this, and it is going to expand everywhere in the near future. And then how to make an impact. Decarbonization is an umbrella, and there are multiple avenues underneath it to make an impact. So you can look at energy efficiency, refrigerant management, renewable energy, electrification. And in all of those segments, there are solutions available today to help customers down that journey. All right, with that, I'm going to hand it over to Kyle, and we're going to start going through some questions.
All right, yes, thank you very much, Charles, Jackie, and Matt, for a great presentation. As you said, our presenters will address some questions that have been submitted throughout the program. If you do have a question, feel free to post it in the Q&A and chat box. With that, we'll get to the first question here. It is from Joe, and it is, will the grid support these electrification initiatives without fossil fuel?
I can take that. Yes, the utility grids across the country, across the world, are keenly aware of what's on the horizon. Electrification isn't a new concept to them. There are places around the world, if you even go to Canada, there are grids that are heavily powered by hydro, and they've been dealing with winter peaks in heating with electricity for some time now. So it is an issue, but they are aware of it, and I'm confident that they'll come up with a solution to manage it.
All right, next one here is from Paul. Don't we have refrigerant management already, and are we going back to ammonia? Paul thinks that would be insane.
Good question. Refrigerant management, I see it a little differently. I see it customer by customer. Everybody chooses to manage their refrigerant differently and at different levels. Some people have very little to do with refrigerant. They put the product in the basement and they never think about it again. Other people are more proactive with it. So are we going to ammonia? Potentially, right? People talk about natural refrigerants. There are certain industries that prefer it. If you go to like the pharmaceutical industry, they prefer natural refrigerants over hydrocarbons. But there are downsides to natural refrigerants as well. Ammonia is toxic and flammable. Propane's really flammable. CO2 isn't the best refrigerant in cooling. So there's pros and cons, and we have to weigh those when we bring new product to market. But refrigerant management is going to be more prevalent across the board, especially with the EPA. I think they're going to require more in terms of compliance in the next couple of years. So Switching to lower GWP refrigerants can limit the impact you have on the environment, and then maintaining your equipment and keeping your refrigerant under control is another way to do it.
Got it. Next one here. How do the new refrigerants perform from a kilowatt per ton perspective?
Great question. Like I said in my section, there's a lot of information out here, and if people are interested in digging into this more, we have more information. Typically, when we switch refrigerants, we go to slightly less efficient refrigerants than their predecessor. Otherwise, we probably would have been using them for as long as they've been around. Now, we've been lucky with this current transition. We have been able to find refrigerants that maintain similar efficiencies to their predecessors. But what I will say is refrigerant isn't the only thing in a piece of equipment. We can go to better compression technologies. We can go to better heat exchanger technologies. We can go to better aero technologies and oil management. So there's a lot of other technologies that play into it, and product efficiencies have continued to get better even though we've been transitioning refrigerant.
All right, James is asking, how do we compare reduced efficiency of the refrigerant versus the increased size and power requirements of the system?
That's a great question. That almost gets into an embodied carbon versus an operational carbon. So if you need more copper, you need more steel to make a piece of equipment more efficient because you're using a less efficient refrigerant, there's a balancing act there. I don't have the numbers off the top of my head, but I can tell you we are constantly trying to play that balancing act and make sure the refrigerants as well as the materials we use have the lowest impact on the environment.
This one here is from Cheryl. What about how to handle defrost? How long does the defrost cycle take?
I'm gonna stop talking and let one of the other people take it.
I'm going to assume that's a defrost question because that happens a lot it's a consideration with VRF. VRF systems do in heating season, have to go into defrost mode every now and again, in which time you're not going to be getting much heat into the space at all. And there's a couple of strategies for that. One strategy that is utilized pretty frequently now is it's almost like a preheat that it'll do. So it'll actually overheat the space leading up to a defrost cycle. So the fan turns off when it flips over into defrost, and then you're not actually blowing any cold air into the space, and tenants don't really notice at all, or occupants don't notice at all. And then I would say another option is you split up your systems in different ways so it's not as noticeable, as well as there's also a continuous defrost setting that most systems employ.
Yeah, we also have defrost when we look at our air source heat pumps. So our new ACX, Ascend ACX, is dual circuit. And so only one circuit goes into defrost at a time. So it's programmed such that defrost will have minimal impact on your heating. And when we look at it from a modular standpoint, we do send the modular units into heating, one at a time. So never at any time is your entire system switched to defrost. So you always at least have a circuit or a module or two in heating. So the impact is very small.
All right, this might be a nice easy one. What is the life expectancy of VRF systems?
ASHRAE has the life expectancy of VRF systems listed at 15 to 20 years typically.
All righty. I love VRFs. This is Cheryl talking. Not that I don't love VRFs too, but the facilities engineers do not like it. Do not like it due to the number of filters to replace. Any suggestions?
Get a service agreement with your local Trane office, and they'll do it for you. I would say, that is, a limitation. You could have fewer, bigger units that are large ducted units you could use, so you're not having a unit in each space, but it's going to be a balancing act, right?
All right, next one here is from Paul. Does simultaneous heating and cooling load minimize the load at the outdoor condenser?
That's right. The load at the outdoor unit, the condenser is going to be lesser if it's just kind of moving refrigerant around. The refrigerant will still circulate by the outdoor unit, but if you're, mixing it around within the space, reusing refrigerant, you're going to be drawing less in from the outside.
All right, Dave is asking, how does the efficiency of a VRF system change at low ambient temps? Do we have to significantly oversize even though the VRF is still able to work at lower temps?
Typically, that's something that's done at design phase. So you design for a certain design condition, and the way that most VRF software works for design, it tells you what you're going to be getting at those conditions, and that's what you'll design for.
All right, and we'll kind of end on this one from Robert. Can this be used with apartment fan coil units using chilled water, hot water?
Probably about hybrid VRF.
Hybrid VRF, right? The answer today is no. The first generation of hybrid VRF that comes to the U.S. will need to use special Mitsubishi or manufacturer-specific indoor units, just because of the amount of communication that goes between the indoor unit and the rest of the system to deliver the proper amount of heating and cooling to the space.
Okay. Hey, that was pretty quick, so we're going to squeeze one more in here if you guys don't mind. How do you maintain humidity in space using VRF systems?
So the modular nature of VRF tends to help with maintaining humidity at proper levels, because it's modular and you're not cycling the system as much. It draws more humidity out of the space slowly, but we typically do recommend pairing VRF with a DOES system or some other sort of ventilation system that helps to control the latent load or humidity in the space, because VRF systems aren't typically designed to control to a certain humidity set point.
Alrighty, well, that's all the time we have for questions today, everybody. So we're going to conclude this webinar. Please join me in thanking Charles, Jackie, and Matt for the presentation, and of course, as well as our sponsor, Train. It was really, really great information, all three of you. If you have any additional questions or comments, please don't hesitate to email us at webinars@bnpmedia.com. As you exit today's webinar, please take a couple of minutes to complete our survey. We strongly welcome your detailed comments. You can also visit us at esmagazine.com/webinars for the archive of this presentation, as well as information about our upcoming events. We appreciate your time and hope you found this webinar to be a valuable experience.